Hello everyone. Now in the previous chapters we have understood about how to perform static structural analysis. Then we have understood how to perform the modal analysis. In static structural analysis we have done a lot of options, we have covered a lot of options. We have understood how to perform static structural analysis on 3D models, 2D models, 1D models, assemblies. We have seen some important concepts in static structural analysis. Similarly, we have understood how to perform modal analysis. We learned what is modal analysis, why we should perform modal analysis, what do we calculate in modal analysis. We saw different types like free vibrations, free vibrations. We saw how to perform a modal analysis on a 3D model, in 2D models. Then we saw how to perform a modal analysis on an assembly. Okay. Now in today's session, we will be starting with buckling analysis, which is the next chapter that we are going to study. Now, when you talk about buckling analysis, first let us understand what is buckling analysis. Okay. So when we apply static loads on a model, it can produce some instabilities due to some combinations of the geometries and the loads. So whenever we are working on a design and we apply some static loads on it, there can be some situations where due to some combinations of loads or the combinations of loads and geometry, some instabilities can be generated inside the design. Okay, buckling of a long slender bar in the axial compressive direction is a common example that everybody gives whenever we perform buckling analysis. So what is exactly the buckling analysis? So whenever we have a long slender object, now what is the meaning of a slender object? As compared to the length, the cross section of the model is very small. Okay. So a long slender object is nothing but when a body has a length, the length of the body is long as compared to the cross section. So such a body is considered to be a slender object. So when we have such a slender object which is subjected to an axial load, okay, it is subjected to an axial compressive load, what will happen is this object will tend to bend like this. When the force is continuously applied, it will tend to bend more. Okay, after some time it will bend more. But at a particular time, there will be one specific time when the model will completely buckle and it will fail. Okay, so we have to calculate at what load the buckling will occur. Okay, so that is why whenever we talk about buckling analysis, the buckling of a long slender bar is generally taken as the most common example. Okay, so in Ansys Workbench, we will be using the linear buckling analysis system to perform the buckling analysis. Okay. Now let us understand some more things about the buckling analysis. Okay. Now whenever there are thin structures that are subjected to compressive load, this is the same thing that we discussed in the previous slide, that whenever we have a long slender object, so thin structures is nothing but slender object, they are subjected to compressive loads, it can buckle under some loading conditions. Okay, so they can buckle under some load combinations. Now the buckling is a sudden failure of a structure when it is subjected to high compressive stresses, where the actual compressive stress at a point of failure is less than the ultimate compressive stress. Okay, so whenever we are applying some compressive loads on a long slender object, there will be some stresses that will be generated. Okay, so whenever the actual compressive stress at a point of failure is lesser than the ultimate compressive stress, the material will fail, and we have to find out at what value of load will this failure occur. Okay, so that entire thing or that complete concept is called as the buckling concept. Okay. Now when you talk about buckling, there are different cases that we can study in buckling. The first thing is, look at the formula over here. The formula for calculating the buckling load is pi square EI divided by KL square. In this, F is nothing but the critical force or the buckling load. E is the modulus of elasticity. I is the area moment of inertia. L is the unsupported length of the column. K is the column effective length factor, whose value depends on the conditions of end supports of the column. Okay. So now we have taken 4 cases of supporting. Okay. Now in the first case, you will see that the one end of the beam is fixed and the other end is free to move in the lateral direction. So in this condition, if you have such a condition in your design, the K value is considered to be 2. So if one end of the beam is fixed and the other end is free to move laterally, K is taken as 2. In the second condition, if one end is pin supported and second end is also pin supported, if both the ends are pinned, okay, the K value is taken as 1. In the third condition, if one end is completely fixed and the other end is pinned, you can see over here, one end is completely fixed and the other end is pinned, K value is taken as 0.707. And the other condition is, if both the ends are completely fixed, the K value is taken as 0.5. So this is the formula by which the buckling load is calculated, and there are some situation in which the K value will change. So according to the loading conditions and according to the constraining of the other ends, the K value changes. So we have understood what are the situation, under what situations the K value changes. Okay. Apart from this, there are some points that you should remember whenever you are performing a buckling analysis. Now, when you are calculating or when you are performing the buckling analysis will only give us the buckling load and it does not find the area of buckling. So when you perform the buckling analysis, it only calculates the buckling load. It does not show the area in which the buckling will occur. So the output that we obtain from the buckling analysis is only the buckling load. Other points that we should remember while performing buckling analysis is that the linear buckling analysis must always be done after a static structural analysis. That means you first have to perform a static structural analysis and then after that you should follow it by the linear buckling analysis. If you only perform the linear buckling analysis, you will not get your results. Okay, so that is the first point to remember. The second point is the results calculated by the buckling analysis are buckling load factors that scale the loads applied in the static structural analysis. That means the output that you get from the buckling analysis is just the buckling load factor. Now this buckling load factor will scale or will get multiplied to the load that is applied in the static structural analysis. For example, if the force applied in the static structural analysis is 10 Newton, okay, assume that in the beam you have a force that is applied is 10 Newtons, and the result after performing the buckling analysis you get the load factor as 1500. That is the load factor that we have obtained after the analysis. So the buckling load will be 10 Newton, that is the force applied multiplied by the load factor. So the answer will be 15,000 Newton. So 15,000 Newton will be your buckling load. This is a very important thing that you should always know when you are performing the buckling load. Hence, we will always, to simplify the results, we will always apply a unit load in the static structural analysis. That means we apply a load of 1 Newton in the static structural analysis. Why? Because when you apply a load of 1 Newton, whatever load factor you get multiplied by 1 is the same value. So it becomes easy for us to calculate and understand. Okay. The next point is buckling load factor is to be applied to all the loads used in static analysis. That means if there are two loads acting, means if there is one load acting from this direction and the other is in this direction, we will have to apply the load factor to all the loads that are getting applied in the static structural analysis. The next point is there can be many buckling load factors in a structure. Okay, that means you can get multiple load factors. But our main interest is in the lowest buckling load factor. That means whichever is the lowest value in the buckling load factor, that is of main interest to us. That means if we are getting the first 5 buckling load factors, the first one, which will be the lowest one, is the main buckling load factor that we will be interested in. Okay, that is why instead of calculating first 10, first 5 or first 3 buckling load factors, we can only find one buckling load factor, which will be the first one and the lowest one. So we can only take that into consideration. Okay. The last point that you should remember is that the buckling mode shapes displays. The buckling mode shape displays helps us to understand how a part or an assembly will deform during buckling. So once you get the mode shape, okay, of the buckling analysis, we can understand what can be the tentative direction of deformation. But it is not the actual representation of the displacement. So please understand, whatever mode shape you get in buckling analysis can be considered as a example, or it can be considered as a reference, but it will not be the actual displacement that will happen in real time. Okay. So these are some important points that you should always remember when you are performing the buckling analysis. Now in the previous session we have already understood what is buckling analysis, what are the outputs that we are going to calculate from the buckling analysis. There are certain points that we need to remember when we are performing buckling analysis, so we have understood that also. Now we are going to solve a problem and understand how to perform the buckling analysis in Ansys Workbench. So for understanding this, we will take the first problem, that is, it is a stepped rod and it is fixed at one end as shown in the figure, and it is actually loaded by 2 forces. You can see 2 forces that are acting over here. One force is acting on the top, which is 1000 newtons, and it is acting in the axial tensile direction, and there is one more load which is acting at this position of 2000 newton, but it is acting in the axial compressive direction. Okay, and we are supposed to find out the buckling load for this particular design. The material that we are going to use for this analysis is structural steel. The large diameter over here is 0.011982. Small diameter is 0.010, and the length of the large diameter is 0.2 meters, and the length of the small diameter is 0.1 meters. So let us perform this analysis in Ansys Workbench. So I will come into Ansys Workbench. Now, if you remember, we discussed one point in points to remember, that is, a buckling analysis, a linear buckling analysis should always be performed after the static structural analysis. So first we are going to perform a static structural analysis. Okay, and I will say linear buckling analysis. And then the material that we are going to use for this example is structural steel. So that is the same material that we get by default, so I don't need to enter into the engineering data. And then I'm going to come into the geometry, and then we will create the geometry. So let us create the geometry first. So as we can see over here, the unit system is into meter. I'll take one sketching plane and let us start sketching. So I'll draw one circle, and then we will give the dimensions for this. So the dimension is 0.011982. 0.011982. 0.011982. So that is the diameter that we've got. Okay, so this is the model that we've got, okay, whose diameter has been mentioned. Now let us come back to the modeling and we will extrude this. So this is the sketch that we need to extrude. and the length of this is 0.2 meters. So I will enter this as 0.2 meters and we will generate it. So this is the model that we got. Similarly, now I need to sketch another model on this face. We will enter into the sketching tab, and again over here I am going to draw one circle whose diameter is 0.010. 0.010, and then we are going to extrude this to a depth of 0.1 meter. Now, because both the step bars have the same material, I will use the add material option. If both of them had different materials, we will have to do it as add frozen. But now I will make it as add material. Okay, so this is the geometry that we have. Okay, so now the geometry is ready. After this, we will enter into the mechanical window. Okay, now once we are here in the mechanical window, the first thing is to check the material, and then we will mesh the model. So I am going to use the default mesh settings. Okay, we can observe over here that we've got tetrahedral elements. Okay, if you wish, you can add the proximity and curvature option so that we get finer meshing over here. Okay, now you can see over here that this region has been meshed very fine. Okay, after this, now we will apply the boundary conditions. So I'll take the static structural node and we will apply one fixed support on this end as mentioned in the problem. And at this particular end, there is an axial tensile force of 1000 newtons. So I'm going to apply a force of 1000 newton in a tensile direction, and there is another force at this face which is 2000 newton, but it is in the opposite direction, a compressive load. Okay, so these are the loading conditions that we've applied: fixed support, tensile load of 1000 newton, compressive load of 2000 newton. Okay, and then I will just add one deformation option over here and we will solve the analysis. Okay. Now once we get the solution, you can check the result. Okay, and then we will exit from the static structural analysis. Now the static structural analysis has been performed, but we are interested into the buckling load. So now what we are going to do is we will add one linear buckling analysis system to the solution of the static structural analysis. So you can select it from the toolbox and drag it to the solution. Okay, this is very important. Left click, use your left mouse button to click, keep your left mouse button pressed and drag it to the solutions cell of the static structural analysis system and drop it there. Once you drop it, you will see the engineering data, geometry, model, and the entire setup and solution has been shared with the linear buckling analysis. And now we will enter into the setup cell of the linear buckling analysis system. Once you come over here, you can see that the meshing, static structural data, the loads, the solution has been taken, and in linear buckling analysis system, here you can see that it is pre-stressed. Pre-stressed, that means the stress has been taken from the static structural analysis. Okay, now click on analysis settings, and here as we change the number of modes to fine in vibration analysis or modal analysis, similarly even in buckling analysis we need to mention the maximum modes to fine. Okay, so here we will say that I only want to find the first buckling load factor, which will be the lowest one. And now we will click on solution node, right click, and we will say solve. So it will solve and it will give the output of a load multiplier. It takes time because of the meshing that we've done. We have used proximity and curvature, because of which we have got a very finer mesh, and due to the same, the run time or the analysis time is taken a longer time. Now when you click on the solution node, here you can see what is the load multiplier. So the load multiplier is 22.967. Okay, so 22.967 multiplied by 2000. So here the load will be 45,934. So at 45,934 newtons, the model will buckle in combination with 22.967 multiplied by 1000. So with a combination of these two loads, the model will buckle. Okay. So this is how you will perform the buckling analysis using the static structural analysis system plus the linear buckling analysis system. Now let us look at the second example for in the buckling analysis. We have a circular arc of rectangular cross section and it is subjected to a pressure load as shown on the figure. So the pressure getting applied on this face is 1 megapascal. The boundary conditions are also given over here. Both the edges over here are fixed support. Okay, and now we have to find out the load multiplier for the first buckling mode. The material that is going to be used for this arc is stainless steel, and the arc cross section is 5 into 15 5 mm into 50 mm. Mean radius of the arc is 50 mm, and the included angle is 90 degrees. Okay, so now in this condition you can see that as per the dimensions are given, the thickness of the model is very small. So rather than creating this as a 3D model, we can consider this to be a 2D model. Okay, so let us see how to perform this analysis in Ansys Workbench. So let us add the static structural analysis system. The material that we have to use for this analysis is stainless steel. So I will come into engineering data, resources, general materials, stainless steel, and we will add this. Okay, now we will return back to the project and we will again come into the geometry. Now once you come to the geometry, observe the unit system. It is into mm. So set your unit systems to millimeter, and now start creating your geometry. So the geometry, we have to create a circular arch of radius 50 millimeters. Okay, so I will take one arc option. Okay, I will give the dimension and the radius is 50 mm. Once this is done, I will draw two lines from here. And the angle between these two has to be let me calculate the angle again. This has to be 90 degrees. And now I'm going to use one constraint symmetry between this. Once this is done, I will trim whatever is not needed. I will give one more constraint. Let me delete this. So this is the arc that we wanted. Okay. So we got the design. Let us come to the modeling tab. And now I'm going to extrude this. Now while extrusion, the depth given is 50 mm again. Okay. So this is the model that we needed. And the thickness of this model is supposed to be 5 mm. Okay. You can also view the model like this. Now once the design is ready, we've understood that instead of 3D model, we are going to consider it as a 2D model and solve it. So the design is ready. We will come to Ansys Workbench project schematic window, and now we will enter into the mechanical window. So the material has to change to stainless steel. So once you change the material to stainless steel, the next is we need to mesh the model. So I will just use the default mesh settings and perform the meshing. So you can see that the meshing has been done. If you wish, you can just change the relevance so that the meshing becomes finer. Okay. And now we will click on the static structural node and give the supports. So we need fixed support on both the edges, which have been applied now. After this, I'm going to again click on static structural node, loads, and we are going to apply a pressure on the top surface, and it is 1 megapascal. And let us solve the analysis. I'm not taking any results because I'm not interested into the static structural results. After the static structural analysis is done, we can exit from here. And the next, we are going to add the linear buckling analysis system to the solution of static structure. So now you will see all the data is shared. You will click on the setup. Okay. Analysis setting, check the number of modes to find, and now solve the analysis. So the analysis is done, and we have also got the load multiplier, which is 587.52. So when I apply this to the pressure, which is 1 unit, that means if I apply a pressure of 587.52 megapascal, this design over here will buckle. Okay, and for this load factor or the load multiplier, if I create the deformed shape, this is the deformation that we will get, and you can perform you can generate the animation for this. So this is the method of performing a buckling analysis on a 2D model. Now let us look at the next example for buckling analysis. Now in this case, we are going to perform a buckling analysis on a 1D model. Now let us go through the problem description first. We have a beam which is fixed at one end and it is subjected to two compressive forces. One of the forces is applied on a portion of the beam of length 50 mm from the fixed end, and the other is applied on the free vertex. The values of the forces are given over here. Force 1 and force 2 are both 1000 newtons and they are acting in the compressive direction. The material that we need to use for this type of this analysis is structural steel. We are going to use a rectangular cross section which is of 10 millimeter into 10 millimeter. The total length of the beam is 200 millimeter, and length 1, that is L1, is equal to 50 mm. The force on L1 is 1000 Newton compressive, and force on the free vertex is also 1000 Newton in the compressive direction. Okay. Now let us perform this analysis in Ansys Workbench. So again I will come to the Ansys Workbench project window. I will add one static structural analysis system. We have to use structural steel as the material, so I am not entering into the engineering data because structural steel is the default material. We will enter into the geometry. Now there is one thing that we need to note over here. The unit is millimeter. Now see, there are two sections, okay? Both the cross sections are same at L1 and at the rest of the area. The cross section of the beam is same, but we need one point in the center which is at a distance of L1 where the force can be applied. So I cannot make the entire beam as one single structure. We need to have a break over here. So for creating such a design, we have a general method. Now let us see what that method is. When you go into sketching, rather than drawing a single line of 200 mm, okay, what we will do is, I will use a polyline. I will draw one line, and again I will continue and draw the other line, and then right click and say open into. So you can see we have two lines. Okay, I'll give the dimensions to both the lines. H1 has to be 50 millimeters and this has to be 150 millimeters. Okay, and then I'm going to add one constraint which is a symmetric constraint to this. So this is how I have created my design. Okay, please make sure that you create it in the same manner, otherwise you will not get a point in the center where you can apply this load. This is a very important step for this problem. Okay, now once this design is ready, now we will create one cross section. So we have to create one rectangular cross section which is 10 millimeters by 10 millimeters, after which we will go and create the line from sketches. So we have this sketch over here, apply, and we have created the line body. After that we will apply the cross section which is the rectangular cross section. So this is how we have created our body. We can view the model. So this is how the model is ready. So now my geometry is ready. We will take this geometry into the mechanical window. So I'll double click on the mechanical window. The model is generated in the mechanical window. Okay. Now once the model is ready, the next thing that we will do is we will perform the meshing. So I will use the default mesh settings. If you want, you can make it finer. Okay. You can see the So now the design is ready. Now we will click on the static structural node. You can see over here. You can change the view options from here, whether you want to see the cross section, whether you don't want to see the cross section. Okay. Now, once I click on the static structural node, I will first add the fixed support. I will use the selection filter of a point and just select this point over here. Okay. So this is a fixed support that we have applied. After that, there is one force which is acting at a point over here. Now see, this is because that I have drawn the polyline into two parts. I have not drawn one single polyline. I have drawn one over here and the other one over here. Because of which now I am getting a point over here where I have to apply the load. The load value is 1000 Newton and the direction of the load is this. And it has to be in the compressive direction. Similarly, direction has to change. my force has been applied. I need to apply one more force at this vertex. It is again 1000 Newton and the direction is this. Swap the direction and apply. So we have got the forces, we have got the fixed support. So these are the boundary conditions that we've got. And now we will solve the analysis. So I'll get the results. Okay. Once the static structural analysis is done, close this window. And now add the linear buckling analysis system to the solution cell of the static structural analysis system. You will see that the data is shared. Enter into the setup. Okay. Now click on the analysis system. Number of modes to find. Here you can also change the output controls if you want to calculate the stresses and strains in the end. After this, you can say solve. So now you will get the load multiplier for this analysis. So my load multiplier is 10 units. That means I need to apply a load of 10,000 newtons to buckle this design. Okay. Now I can generate the deformed shape. Okay. Once the deformed shape is ready, you can also check the deformation, and then I can also add the beam results, and we can check the stresses. Okay. So you can check your answers over here. So this is how we will perform a linear buckling analysis on a 1D model. Okay. In the previous example, we have seen how to perform buckling analysis on a 1D object. Now in the next example that we are going to take, we are going to perform a buckling analysis on an assembly. Now if you see on your screen, you can see the assembly design is given over here. It is a component of a truck dumping mechanism, and which is placed in compression when in service. Means when it is operating, there is a compression load acting over here, and all the components in the assembly are welded. They are all simple structures. If you can see, there is a block over here, there are some L brackets, and there is one pin rod over here, which are simply welded and created. So the analysis that we have to do is we have to perform a buckling analysis on this design. The load acting on this design and the boundary conditions are mentioned over here in the image. And the material that we need to use for this assembly is structural steel. The assembly contacts that will be created in the assembly are all bonded contacts except the contact between the pin and the L brackets. Okay. So now we know what are the conditions in the assembly, we know what are the loads acting on the assemblies. So let us perform this analysis in Ansys Workbench. So we've come to the Workbench software. We will first add one static structural analysis system over here. The material that we need to use for this analysis is static structural steel, and then we will import the geometry. Now the geometry, either you can create the geometry or you can import it from any other CAD software. So let me import this geometry. So this is the geometry that we have to import. After the geometry has been imported, you can double click on the geometry cell and enter into the design modeler. Now once the geometry has been imported, you can check the models. You can see that there are 6 components over here. You can see all the components. Okay. Now after the geometry has been imported correctly, then you can exit from the design modeler and you can enter into the mechanical window. So double click on the model cell to enter into the mechanical window. So we've got the assembly into the mechanical window now. You can first check the material. Now because all the parts in this assembly are made up of structural steel, you can select them simultaneously using the control button, and then you can change the material for every component. Okay. After that, then we will have to check the connections. So we have the connections over here. So as mentioned in the PPT over here, all the contacts, all the assembly contacts are bonded except that between the pin and the end brackets. So you can see over here, the eighth region, contact region, is between the pin rod and the bracket, and we have the fifth contact region which is between the pin rod and this bracket over here. Okay. So I need to change this. I am going to allow some motion between the brackets. So I'll change this to no separation, and also contact region 8 to no separation. Once that is done, apart from this, all the other contacts will be, by default, it is going to be bonded. Okay. So now that we have changed the contact regions and the definition of contacts, after that, the next step we will perform the meshing. So let us update the meshing and perform the default meshing. So the default meshing that we get is going to be coarse. Okay, so you can see that the mesh has been performed now. Now the meshing that has been created over here is the coarse meshing. You can use the local mesh settings, the sizing option, to give a sizing for every component. You can select the component, and then you can give a default element size for this. So I'll say that the element size is of 20 units. Update the meshing. Similarly, I can give another sizing for these L brackets and these strips also, plus everything. Okay. And I'll perform the the meshing has been completed. You can see over here. So now you can observe that the meshing is quite finer and better than we got in the first attempt. After the meshing has been done, now the next part, we will apply the boundary conditions. Now in the boundary conditions, we have a support at this end at the circular holes, which is going to allow the rotational motion at the holes. So for allowing the rotational motion at the holes, we will take one cylindrical support. Now this cylindrical support is going to be at these circular holes. The cylindrical support is generally used for circular objects. Let me show you that. Suppose if you have a cylindrical hole over here, and if you want to use the cylindrical support, now whenever you use a cylindrical support, you will get three connections, three options to control the motion. So we have three motions that will come. We will have the axial motion, the radial motion, and the tangential motions. So this will be the axial motion, which will be in the axial direction. We have the radial motions, which will be in this direction and in this direction. And finally, we have the tangential direction, which will control the rotational motion. Okay, so these are the three options that you will get in a cylindrical support. So now let us see. You can see that there are three options: radial, axial, and tangential. Okay. Now in this condition, I just need to allow the rotational motion. So if you see that the axial axis is the x-axis, I need to allow the rotation about the x. So that motion can be controlled by the tangential option. If you want to allow this motion, you will keep this motion to be free and the others to be fixed. So when I say this, when I select these options, it means that only the rotation about x will be allowed. Okay. After that, the next constraint that I'm going to apply is a remote displacement. Now, remote displacement, when we select this option, we get all the 6 degrees of motion which we can control. And in this condition, I'm only going to allow the lateral motion for this assembly. That means I'm going to allow the motion only in x and the y direction. So this assembly can move or can translate in the x and the y direction. It cannot translate in the z direction. And the rotational motion along x, that means if the assembly is like this, if this is the assembly, we have this as y, this as z, and x is pointing towards us. So it cannot move in this direction. It cannot rotate about y, or it cannot rotate about x. So if you consider this to be x, the rotation is going to be like this. So it cannot rotate along x directions, neither it can rotate along the y direction. If you see over here, it cannot rotate about y. Okay, only rotation about z will be allowed. That means if it is rotating along z, the motion will only be in the xy plane. So this is the lateral motion that I'm going to allow for this assembly. So let us apply these constraints now. X and y is going to be free. Z translation is going to be fixed. So we will keep that as 0. Let us first select the geometry. I'm going to select this and this over here. Okay. Then rotation about x and y, both are going to be fixed. So we will keep that also as 0 degrees. So with this, now we have applied one remote displacement constraint which will only allow the motion of this assembly in the xy plane. Okay. After that, then we will apply a load. We will apply a force of 1 Newton. We will apply a force of 1 Newton in the downward direction. It is going to be a compressive load, axial compressive. And then we will solve this assembly. So let us say, so I don't need any results because I'm going to perform a buckling analysis. So the results have been captured. It has finished the analysis. After this, we will then add one linear buckling analysis to the solution of the static structural system. Once you do that, all the data gets shared. You will enter into the setup. And now in the setup, you will first give how many modes to find. Okay. And after that, we can solve this analysis. So when this analysis is getting solved, you will get the load multiplier for this analysis. Now you can see that the analysis has been done and you have got the load multiplier of 56,732 units. So that means that if I apply a force of 56,732 newtons on this design over here, this assembly is going to buckle. Okay. So with this, now we've understood how to perform a buckling analysis on an assembly. Now, after the buckling analysis, the next chapter that we will learn is thermal analysis. Now, thermal analysis is a different topic that we are going to start, in which the body that we are going to analyze is going to be subjected to thermal loads. And there are different types of analysis that we will be performing under thermal analysis. So let us understand what is thermal analysis first. Thermal analysis is the most important analysis through which a design has to pass before manufacturing. Apart from the structural analysis, where we are understanding the displacements, stresses, deformations, all these things, thermal analysis is also important for a design, because you need to understand whether the design that you are creating will be able to sustain the temperatures that are being induced in the body. So that is why it is also one of the most important tests that a design has to pass through. Thermal analysis is used to analyze the temperature distribution and related thermal quantities. So when we are performing the thermal analysis, we understand what is the maximum or minimum temperature distribution in the design and where exactly in that design it is happening. Apart from the temperature distribution, there are other thermal quantities that we will be analyzing or we will be calculating using the thermal analysis. For example, thermal flux, thermal flow, amount of heat lost or amount of heat gained. So all these are different quantities that we can also calculate using the thermal analysis. Thermal analysis is used in many engineering domains such as automobile, piping, electronic power generation, and many other. So it is not only related to any one specific industry, it can be applied or it is used in many industries such as automobile, piping, or electronic power generation. Whenever a body is subjected to thermal loads such as temperature, internal heat generated, temperature is induced in the body due to the heat transfer. So whenever we have an object, if we have a design and it is subjected to a thermal load, for example temperatures, or internally heat is getting generated in it because of some other input, such as when you, for example, when you charge a mobile battery, you are heating the you are not heating, you are charging your mobile phone using the electricity, but due to the charging, the battery gets heated up due to the heat generated inside it. So that is an example of heat generation, due to which temperature is induced in the body. So we will be learning about what are the different types of heat transfers, because when you talk about temperature induced, it happens because of the heat transfer. Whenever heat gets transferred from one object to the other, temperature is induced. So when we are learning about thermal analysis, we will be also talking about the different types of heat transfers, and we will be seeing some examples using which we will calculate the temperatures, heat loss or heat gain, thermal gradients or thermal fluxes. So let us talk about the heat transfers first. What are the different types of heat transfers? There are three major types of heat transfers: conduction, convection, and radiation. So let us discuss about conduction first. Conduction is the process of heat transfer between the bodies in contact. Whenever two bodies are directly in contact with each other, you can see the image over here. Just one second. Now you can see that whenever two bodies are directly in contact with each other, now this body over here, that is T2, where it is getting heated up at a temperature T2 which is higher than or more than T1. So the heat will flow from higher to lower. So this is an example of conductivity where two bodies are directly in contact with each other. The medium of contact is a solid. Okay. So when you talk about the heat transfer, the formula that we consider in conduction is Ka delta T, where K is the thermal conductivity of the material, A is the area of contact, and delta T is the change in temperature. Okay. So this is about conduction. Next is convection. Convection is a process of heat transfer in which the medium of heat transfer is a fluid. When you say fluid, it can be a liquid also or gases also. Fluid does not mean anything has to be liquid, but it can be liquid plus gases also. So there are different examples of convection. For example, when you are heating water using a heating rod, electric heating rod, that is an example of convection. When when you keep a cup of tea for some time, the tea becomes cold. That is because the heat from the tea is getting transferred to the outside ambient temperature. So even that is an example of convection. When you talk about convection, the formula that we will use is Q is equal to HA delta T. A delta T is nothing but it is a difference in temperature, the surface temperature and the ambient temperature. Okay, ambient temperature is nothing but the atmospheric temperature which is surrounding that object. Okay, where Q is the amount of heat transfer, H is the film coefficient, okay, and delta T is the change in temperature. Now let us talk about radiation. Radiation is a mode of heat transfer in which the heat is transferred through space. Okay. Now whenever the heat is getting transferred in space, we call it as radiation. The best example of radiation will be the sun rays which get transferred to the earth. The other examples can be when you are heating something inside a microwave oven, or the electromagnetic waves, or your light waves. Okay, all these are examples of radiations. Even your X-rays are examples of radiations. Now the formula that we consider, or that is used to calculate the radiation, heat transfer due to radiation, is Q is equal to emissivity into sigma, that represents Stephens-Boltzmann constant, A, that is the area, and T raised to 4, hot means whichever medium is hotter, that is going to transfer heat to the colder medium. So it is a temperature difference between the hot medium and the cold medium. Now in this case, the surface emissivity is represented by this symbol over here. Now when you talk about radiations, there are two types of bodies. Whenever a body is being radiated with energy or some rays, if it is a perfectly black body, it will absorb everything that is radiated on it. So the emissivity is it does not radiate anything back. It absorbs everything. So in that case, the emissivity is 1. Okay, but if it is it's not a black body, it is a gray body, then in that case emissivity will be something lesser than 1. So if it is radiation, if you're talking about radiations on a perfectly black body, emissivity becomes 1. So the formula becomes sigma, that is Stephens-Boltzmann constant, area, and T4, that is a temperature difference. Okay, so these are the different types of heat transfers that we need to know before we start with thermal analysis. So the three types of heat transfer are conduction, convection, and radiation. In our syllabus, we are going to talk about conduction problems and convection problems. Then let us talk about the different types of thermal analysis. There are two major types of thermal analysis, that is steady state thermal analysis and transient thermal analysis. When you talk about steady state thermal analysis, in this type of analysis, the temperature acting on the body does not vary with respect to time. That means it is constant throughout the analysis. And when you talk about transient thermal analysis, it is that type of analysis where the temperature acting on the body varies with respect to time. Okay, so we will be seeing both the types when we solve the problems. Okay, so this is about the thermal analysis. We have understood about the basics of thermal analysis. What is thermal analysis? Why we are performing the thermal analysis? What are the outputs that we can calculate when we are performing thermal analysis? And then we have spoken about the heat transfers. Apart from this, there are many other basic definitions that are given in the reference guide. You can just go through that once because they are all basic definitions related to specific heat, emissivity, Stephens-Boltzmann constant, or your film coefficient. There are basic definitions. So kindly go through that once when we start practicing thermal analysis. Okay. Now in the next video we will understand some examples on thermal analysis. Now in the next session we will study an example how to solve the thermal analysis. In the previous video, we have already understood about what is thermal analysis and the basics about thermal analysis. We have also understood the different types of heat transfers. So in this example, we are going to consider a gearbox housing which is mounted on a gearbox. Now when this gearbox housing is mounted on a gearbox, it is subjected to some temperature loads. Okay. Now the temperature loads are mentioned over here. The outside region of the gearbox housing is subjected to a temperature load of 60 degrees Celsius, and the interior surfaces are subjected to a temperature of 90 degrees Celsius. Okay, and we also have some convections. So what is going to happen? This object over here that you see on your screen, it is going to be subjected to some temperature loads, and while that is happening, it is also giving away heat to the ambient temperature. So the convection on the outside area, on the outside surfaces of the gearbox housing, it is subjected to a convection of stagnant air. Now the outside atmosphere is air, so the coefficient, we will understand how to apply that, how to apply this condition in Ansys Workbench. The ambient temperature is 20 degrees Celsius. Okay, so this is what we have. We know the data now. The material that we are going to use for this gearbox housing is aluminum alloy. Okay, so now let us see how to perform this analysis. So we will come into Ansys Workbench. Once you come into Ansys Workbench, we will add one steady state thermal analysis. Now in this problem description, it is not mentioned that if the temperature acting on the body is for a specific time. So we will consider this to be a steady state analysis, right? So we will come to Workbench and I will add one steady state thermal analysis. We will change the name. The material that we are going to use for this analysis is aluminum alloy. So first let us add the aluminum alloy. Okay. Now please make sure that the material that you are adding should be from the thermal materials, because if you take it from the general materials, it might not have the thermal data into it. So it is very important that you take it from the thermal material. So make sure you click on the thermal material data source and then you can take the material. Okay. Or else when you go to the general materials, when you add the aluminum alloy, you can check whether this material is having the thermal properties. So it is having the thermal properties. Okay, it is mentioned over here. Okay. Now we will return back to the project. And now we will enter into the geometry. Now the geometry that we have to use in this example is a gearbox housing. We can create it in the CAD software. So we have already created this. And now we will import this. Once you import it, you can double click in the geometry. Set your unit systems and then generate the model. Once the model is generated, you can perform some optimization process. For example, I don't need these cutouts or these slots, so I can just remove them. So I'll come to tools option and we will use the fill tool to fill this. Okay, similarly, I will also fill the other side. Okay, then we will use the Boolean operation and we will unite all these geometries. Okay. After this, if you want to perform some changes over here, we can do it. Now in this, after you have made all the necessary changes, now let us perform the analysis. So for performing the analysis, we can enter into the mechanical window. if you see, the model is exactly symmetrical. So you can also cut the material in the center over here about the ZX plane, and you can take half of the model. Okay. So all these things can be done. Later on, we will come into the model cell. Now when you come to the model cell, first let us understand what tools are available. Okay, so the model is open now in the mechanical window. Now this is the window that is opening when we enter into the mechanical window of thermal analysis. Now you can see over here, almost the window looks same, but the only thing is when I click on the steady state thermal node over here, the contextual toolbar shows all the thermal loads that can be applied on the body. So we have temperature, convection, radiation. If you click on this button over here, heat, you can apply heat flow, you can apply a perfectly insulated body, heat flux, or internal heat generated. And there are some other conditions also which we can use for our analysis. Next, because it is a steady state thermal analysis, you will observe that the run time or the analysis time is only 1 second. Okay. If you remember, we discussed the same thing in static structural. In static structural also we discussed that the run time means the analysis time is only 1 second. Okay. So we have understood this. So the first thing after we come to the mechanical window, we will apply the material that we need for this model. So the material has been changed to aluminium alloy. After that, we will mesh the model. So I can first create the meshing or generate the meshing using the default mesh settings. You will observe that the meshing is quite coarse. Okay. If you are not satisfied with the results of meshing, you can use the relevance option, or you can use the advanced size function, proximity and curvature, and in that you can use the default settings. We will see what results we will get. This might take some time because there are a lot of curved areas and small areas in the geometry. Okay, so you can observe over here that the meshing has been done. It has been refined in the small regions. You can see over here, wherever we have small areas, curved areas, there the meshing has been refined. Okay, the number of elements that has been generated now is 3,48,000 something. You can also check the element quality. We will have all the tetrahedral elements over here. So you can see the quality is quite good. We have somewhere around 0.6. Most of the elements are very close to the perfect shape. Okay, so we can see the quality, check the quality, and after all these things, then we can proceed with our analysis process. Okay, so let us continue. After the meshing has been done, now let us apply the loads. After the meshing has been done, now let us apply the loads. So in this condition, we have a temperature of 60 degrees on the interior surfaces of the gearbox housing. So we will click on the steady state thermal node and we will apply a constant temperature. So take the temperature option, select the surfaces. Okay, so we are talking about this surface where you need to apply a temperature of 60 degrees. Okay, so we will select that and we will apply, and now we will enter the magnitude of the temperature. So we will say it is 60 degrees Celsius. In case the temperature is given into kelvins, you can come to the units option and you can change the unit of the temperature to kelvins, whether you want it in Celsius or into kelvins. Okay. Next, it is said that there is a temperature, constant temperature of 90 degrees, which 90 degrees Celsius is acting on the interior. Okay. So we will go to temperature again, and now I have to select the interior areas. So we are going to select these areas. Okay. So all these surfaces which are there internally, they are going to be subjected to a constant temperature of 90 degrees Celsius. So let us apply it, and we will say it is 90 degrees Celsius. Okay. Now once that is done, after that it is also said over here that the exterior surfaces are subjected to a convection of stagnant air. So now what does this statement mean? If you notice in the problem, they have not mentioned the film coefficient, they have only said what is the condition in the exterior. So in the exterior condition is that of a stagnant air. Now there is an advantage in Ansys Workbench. If you know the situation of the atmosphere, you can directly import the values. Now see what we are going to do. We will add the convection option. Okay. First we will have to select all the exterior surfaces. So we can use the control key and you can just drag your mouse, so you can select all the exterior faces over here. Okay, you can select them one by one, or you can just drag your mouse on them so that they get selected. Okay, see to it that you select all the faces. This surface, this surface. So because there are a lot of faces, it might take some time. Okay, make sure you've selected all the faces. Okay, now we can observe that we have selected all the faces on the exterior, and now we will say apply. We need to mention the film coefficient and the ambient temperature. Now we know that the ambient temperature is 20 degrees Celsius. So let us enter that ambient temperature of 20 degrees Celsius. But the film coefficient we are not sure. But the only thing that we are knowing is that the outside ambient atmosphere is of that of a stagnant air. So you can click on this arrow over here and you can say that we need to import the convection values. When you come over here, there is some inbuilt convection data that is available in Ansys Workbench. Now you can see over here, we have stagnant air options and stagnant water options. Stagnant air, horizontal cylinder, simplified case, vertical planes, and stagnant water, simplified case. Now what does this mean? Whenever you say that it is stagnant air, you can select out of the stagnant air option, or whenever it is a liquid, whenever the object is surrounded by some liquid, that time you can select the stagnant water, simplified case. Okay, and stagnant air, and then you have the orientation of the geometry. For example, the object that we are analyzing, okay, the object that we are analyzing is in a horizontal manner, or it is in a vertical manner. Okay, so now in this case the gearbox housing is something like this. Okay, so I can consider this to be a horizontal case. Or if you are not sure about the orientation of your geometry, you can simply take it as a simplified case. Okay, so now here you can understand that the data is stored over here. You can select that and you can say OK. So once you say OK, you can see over here that the film coefficient has been taken in the form of a tabular data, and you can see the value over here in the tabular data. So at 21 degrees Celsius, the convection of this atmospheric air is going to be this much. Okay, so this is an advantage that we have in Ansys Workbench, where if you know the condition outside, what is the ambient atmosphere like, whether it is air or it is some kind of a liquid, we can directly import these values from the data. Okay, so now the boundary conditions have been applied. You can see very clearly there are three loading conditions: temperature 60 degrees Celsius, temperature 1, temperature 2 is 90 degrees Celsius, and we also have convection. Now we are going to solve the model. So for results, we need to find out the temperature distribution in the design. So I will select the solution node. Now if you see the contextual toolbar, you have thermal options. You can find out the temperature, total heat flux, or the error. You can also use the probe option to find out the reactions. Okay, so now let us see. I can select the solution option, thermal temperature. So this is going to show me the maximum temperature distribution and the minimum temperature distribution in the entire geometry. If you wish, you can also add temperature distribution for one particular region. For example, I am only interested in the temperature distribution in this area. Okay, I am only interested in these two areas. I can add that. So instead of all bodies geometry, I can select these two faces and apply. So now this probe over here, or this result, is going to give me temperature distribution only in these two areas. Okay, now let us solve this. So again, now this will take some time because of the number of elements that we have generated. The meshing is very, very fine. Okay, so now the analysis has been done. We can click on the temperature option over here and we can see the temperature. So it is showing you that the maximum temperature is 90, the same that we applied internally over here. Okay, and now if I can see over here only this region, how much is the temperature distribution in this region. Okay, so this is how you can find out what is the maximum temperature distribution in the model. You can also request for the total heat flux that is generated. So I can solve this and we can understand what is the total heat flux in the model. So when you click over here, you will understand what is the total heat flux. So the total heat flux that is generated over here is 117.28 watts per millimeter square. Okay. Now whenever you talk about heat flux, you can see the arrows over here. Can you see the arrows in the contextual toolbar? When you click on the arrows, it will give you a graphical representation of the area from where the heat is flowing. Okay, the arrow size is quite small. You can increase the arrow size. Okay, you can increase the arrow size so you can clearly see them. Okay. And then you can see the animation over here, which will show from where and how the heat is flowing inside the design. So you can see in the animation. Okay. This option is only available when you have the total heat flux option. Okay. So this is how you will perform a simple thermal analysis for your design. In the previous example, we saw the thermal analysis of a gearbox housing. Now the second example that we will study is a thermal analysis on a heat sink. If you look at the problem description, the heat sink is subjected to a heat flux of 0.01188 watts per millimeter square, and there is a convection on all the other faces. You can see the surface on which the heat flow is acting, which is marked in the image over here. The material that we are going to use for the heat sink is aluminium alloy, and the convection in all the other faces is stagnant air correlation. Okay, so again in this case we will be using the convection data that is available in the Ansys Workbench software, and the ambient temperature that we will consider is atmospheric temperature, whatever is the default atmospheric temperature. Okay, so now let us perform this analysis in Ansys Workbench. We will come to the software. Again, this is a steady state thermal analysis. We need to add the material aluminium alloy. So I will take the aluminium alloy, return to the project, and now we have to import the geometry. Again, this geometry has been created using a CAD software. So let us import the geometry. We have the heatsink model over here. Let us enter into the geometry. Set the unit system, and now we will generate the model. So once you generate the model, you can see that the heat sink has been imported into the design modeler. Now if you have a look at the design very carefully, it is a symmetrical design. Can you see? If we consider the XY plane, about the XY plane also it is symmetrical, and about the YZ plane it is also symmetrical. So rather than taking the complete model, which will take a very long time for meshing and also solving, we can cut it into half. Like you can use the symmetry tool and take 1/4 of this design. For this, what we are going to do is, we will first see whether the planes are properly situated. So no, it is at this side. We need them at the center, right? So first we will have to understand what is the distance. So let us go to the new plane option. I'm taking it from the YZ plane, offset in the Z direction, and enter the values. You can see the displacement. Okay, it has to be, let us say, 75 more. Okay. So we have got it in the center. Now I will say generate. So there is one plane that we've got over here, and we need a similar plane over here in the center. So for that, I'm going to displace the XY plane. So again, the offset direction is in the Z direction. Okay. Now let us enter the values. In this case, it is 5. Okay. You can generate this. In this case, you can use your edge tool selection. Select any edge over here. It is 76, so half of 76, you can find out the value. So this value is not 35. So half of 76 would be 38. Okay. So now we have both the planes. So we will come to tools, symmetry option. I need to have the symmetry about 2 planes, and now select the planes. Plane 4 and plane 5, and generate. So this is the half model that we have generated. Okay. Now we will perform the analysis on this model, right? Okay. So symmetry has been done. We created the symmetry model. Now we will enter into the mechanical window. So once you come to the mechanical window, you will perform the analysis. geometry has been imported. You can see the geometry. I need to change my material to aluminum alloy. Okay. After this, we will mesh the model. You can also see the symmetry region that is available. So let us mesh the model first. I will use the default mesh settings. So with the default mesh settings, you have got pod meshing over here. You can use the relevance option to make it finer. Okay. Now once the meshing has been done, after this, now we will start applying the boundary conditions. Now the first thing that we need to see is the load acting on this face is a heat flux of 0.01188. Okay. Now it was on the entire face, but what we have done is we have cut the model into half. So we have taken 1/4 of this face. So what we are going to do over here is we will also divide this value of heat flux into 1/4. Okay. So for that you can use your calculator. 0.01188 divided by 4. So the heat flow that is going to act on the surface would be 0.00297 watts per millimeter square. Okay. So come back to the mechanical window, select your steady state thermal node, and we will apply a heat flux on this particular surface, and value of it is 0.00297. 0.00297 watts per millimeter square, right? After that, they have also mentioned that there is convection on all the other faces. So we need to select all the other faces for convection. So I'll take a convection tool from here, and I need to select all the other faces apart from this face. So I'll use my control key and start selecting all the faces. Make sure you don't select this face. Okay. There are small faces inside. You can select them all. You don't need this. After applying the convection, you can see if we have left out any other surface. Make sure you select all the faces so that we get correct results. So now we have selected all the faces. Okay, right. So I'll say apply. All the faces have been selected except the one on which you have applied the heat flux. Okay, now the surfaces have been selected. Now the temperature value of the atmosphere is not mentioned, so I will take it as the ambient temperature only, that is 22 degrees Celsius. And in film coefficient, I will again import the value and I will say it is stagnant air simplified case. Okay. Once that is done, then we will come to solution and we will solve the analysis. Okay. So now again I will take the temperature, maximum temperature. I'll take the heat flux, and now I will come to the probe option and I will add one reaction. But let us first perform this, then we will understand what is the reaction option. So you can see the analysis has been done. Let us have a look at the temperature. So in this case, the maximum temperature induced in this heat sink because of the heat flow is 34.106 degrees Celsius. The total heat flux generated is 0.008911 watt per millimeter square. Okay, that is on all the other faces. Okay, now again for the heat flux, instead of the entire body, I can only select the area where I am interested. Okay, I only want to see what is the heat flux on this region, and I can solve. So you can see, you can use the probe option to select any area or any location to see what is the heat flux at that region. Okay, you can see the maximum and minimum probe also. After this, now we will see what is the reaction option. So when I click on reaction, you can understand what is the reaction on the body because of the convection. So when there is a convection happening, what is the reaction in the body? So now I can solve this. Now you will see that because of the convection, there is a heat loss of when you see a negative sign, that means the heat is getting lost. Okay, so it is 1.8509 watt. So that is the amount of heat that has been lost from the surfaces because of the convection. Okay, so this is how you will understand the different thermal quantities. You can also check the other quantities that are related to thermal analysis. Okay, fine. So this is how we will perform thermal analysis on the geometries, and these are the different types of results that we have understood or we have calculated. Okay. Now the next example that we are going to study is, it is a motor housing cover which is made up of polyethylene, and it is subjected to a heat flow of 5 watts for 10 seconds on all the inner faces. Okay, and the convection among the outer faces is of stagnant air, where the ambient temperature is 25 degrees Celsius. We are supposed to calculate the maximum temperature induced and the amount of heat lost or heat gained. Now in this case, if you notice that the load, that is the heat flow of 5 watt, is acting on the body for 10 seconds. That means time is coming into picture over here in this example. So this is a transient thermal analysis that we have to perform. Okay. So now let us understand what is transient thermal analysis. As we discussed previously, transient thermal analysis is nothing but that thermal analysis in which the temperature acting on the temperature loads acting on the body are time dependent. Okay. So now let us see how to perform this analysis in Ansys Workbench. So we will come to the Ansys Workbench software, and now in this case I am going to add transient thermal analysis system to my project window. Okay. Now in the problem it is mentioned that the material that we are going to use for this cover is polyethylene. So we will add that material, and then we will return to the project. Okay. We will just study the material properties. You can see over here that the thermal conductivity is present. Okay. Now let us add the geometry. Now again in this case the geometry has been created in the CAD software. So we will just import that. So now the geometry has been imported. Just have a look at the geometry, whether it has come properly or not, whether if there is any data loss. We will set the unit system, and then we will generate the geometry. So you can see that the geometry has been imported correctly. Okay. Now again in this case the thickness of the model is very small, so either you can consider this to be a 3D problem, or you can also solve it as a 2D problem. Okay, but we will consider this to be 3D only, so that I am able to apply these loading conditions properly on the inside and the outside surfaces. Okay, now that the model is ready, we will enter into the mechanical model. Now when you are performing the transient thermal analysis, all the steps remain same except the analysis settings. You need to specify the time and the time steppings correctly so that you get the correct results. Okay. So the first thing that we are going to do over here is we will change the material for the model. So I'm going to apply polyethylene material. Then we have to mesh the model. So I will click on mesh and I will update the mesh so that I get the default meshing. Okay. Once the default meshing is done, you can change it to proximity or you can change it to curvature so that the meshing is finer. Fine. So once the meshing has been done, now we will click on transient thermal node and we will apply our boundary condition. Please understand, the heat flow that is acting on the body is for 10 seconds. Okay. So now see how to perform this. We need to take a heat flow, select the face where it is acting. It is acting on the inside faces. So we have selected the inside faces. Okay. And it is the value is 5 watts, but it is acting for 10 seconds. So now where do you enter the timing? If you notice over here, it is only for 1 second. So to increase the time, what you need to do is click on the analysis settings option, and here you can see in the details of analysis settings, you can see number of steps as 1. So change this to 10. As soon as you change this to 10, you will see steps and the end time. So you can see that the end time is now 10 seconds. Okay. After this, you have to specify the steppings, means from 0 to 1, how should the time vary? Means do you want to record your results for each second or at 0.5 seconds or each milliseconds? How do you want to record your results? So for that, you need to specify something which is called as automatic time stepping. Now this is very, very important so that the software knows how do you want to record your results. Okay. So by default, this option is always on program control. When it is on program control, the time steppings are controlled by the software. If you see, the time stepping over here is 1 e raised to minus 2. That means the stepping is 0.01. Okay. So the results will get recorded as 0 to 0.01, then 0.02, 0.03. So you will get in 1 second only, you might get somewhere around 650 to 100 results. So you will get a lot of results. But if I don't want such a small time stepping, you can change it on your own. So for changing it manually, you should change this option to on. Auto time stepping should be on, and then now we can manually change these values. Okay. Now when you see, currently we are on step number 1. That means we are going to edit step number 1. So from 0 to 1, I need to have the time stepping as 0.2. The maximum and minimum should be same, and time step should be of 0.2. So I've kept everything on same so that the time stepping is of 0.2. So the answers will get recorded from 0 to 0.2, 0.4, 0.6, 0.8 and 1. So in 1 second you will get 5 results. So total for 10 seconds I should get 50 results. Okay. But now the same thing has to be done for first step, second step. Okay. So each and every time I will have to come over here and change it. So instead of changing it one by one, if you want to have the same time stepping for all the steps, select them all, select over here, right click, say select all steps, and then come over here in automatic time stepping, switch it on, and then give that time stepping. I'll say it has to be 0.2, 0.2 and 0.2. So now whatever we have done over here has got applied to each and every step. You can see, you can click and you can notice the changes. Okay. So this is a very important step in transient thermal analysis, where you need to mention the number of steps which decides the total number of time, and then you have to change the time stepping over here. The same changes you can also do, or the same steps you can also apply in transient structural analysis, where the force will vary with respect to time. Okay, so it is the same thing you can also use in transient structural. Okay, now that we've understood how to set the time, we have also set the time. Now we will again click on heat flow. So you can see the heat flow, the time steps has increased to 10. Okay. Now let us say if it is constant throughout the analysis, we will keep it as 5 only. Or else let us say at 0 seconds the values are different. We can change it like that also. Initially we will just keep it like this. And now we have to also apply convection. So there is convection on all the outside faces. So we have selected all the outside faces. Apply. The ambient temperature I mentioned is 25, and again in this case I am going to import my convection data. Okay. And then we will solve. So for results, in the results we are interested into the temperature induced and the amount of heat loss or heat gain. That I can calculate using the reaction. So let me add the temperature, flux and the reaction. So due to convection, what is the amount of heat loss? Now let us solve. So if a heat flow of 5 watts is applied on the object for 10 seconds, what will be the results? So you can click over here and you can see that if the heat flow of 5 watts is applied for 10 seconds, the temperature induced is 27.649 degrees Celsius. The reaction probe, you can see the amount of heat lost or heat gained over here. Okay, and the max heat flux is this. You can see the vector plot. Arrows will be visible, and you can see the animation which will show the direction of heat flow. Okay, so this is how you will perform a transient thermal analysis. Now let us say, you can see over here the results that have been recorded. Totally we have 50 results. So we have in between also at 1.8 second, what is the result? And I can retrieve this result. So I can say, I can see very clearly at what time what is the result. See, you can see over here. Let us say I want to see the result at 1 second, at the first second. I can right click and say retrieve this result so that the plot changes according to that. So we can see minimum and the maximum temperature both. Okay. Now let us assume that the heat flow, according to the problem, we don't have any changes. But let us say if I want to change, at 0 second the heat flow is 1.2. At 1 second the heat flow is 1.8. Then it increases to 2.2, 2.5, 3.2. So I'm changing at every second. 4, 4.2. Okay, then it becomes 4.5, 4.8, and finally 5. So I have changed the heat flow values at every second. So you can see the graph of the heat flow. And now if I solve my analysis, So previously when we saw it was 27, maximum temperature induced was 27 degrees Celsius. Now let us say how much is the temperature. So it is only 22.36 degrees Celsius, 362, right? Because starting from 1.2, it gradually increases to 5. Okay, so this is the temperature distribution. If the heat flow is also gradually increasing. Okay, fine. So this is how you will perform a transient thermal analysis in Ansys Workbench. In the previous chapter, we have understood about thermal analysis. We understood some basic concepts about thermal analysis and what are the different types of heat transfers. After which we saw how to understand or how to perform a thermal analysis in Ansys Workbench. Now the next chapter that we are going to start with is thermal stress analysis. Now first thing, before we start analyzing or we start performing the thermal stress analysis in Ansys Workbench, we need to understand what is thermal stresses. Now whenever a structure is heated or cooled, it will expand or it will contract. If this expansion or contraction is restricted by some boundary condition, thermal stresses will be induced in the model. Now let us understand this by an example. Suppose we have a simple rod, it's a circular rod that we have, and we are heating it. We are applying some temperature over here and we are heating it. Now due to this heating, what happens is, the material or the elements over here, they will start expanding. Okay. Now because of this expansion, now suddenly if I fix it or if I apply some boundary conditions over here and if I fix this, what will happen? There is no space for this object to expand. Because of this restriction, what will happen? Thermal stresses will be generated over here, or it will be induced in this. So now this stress that is induced in the body will not be calculated. You will not be able to calculate this in the thermal analysis. That is why we need to use another analysis system just to find out or just to calculate the stresses that are induced in the body because of the temperature applied. In this case, we have not applied any forces or pressures for the stresses to get induced, but the stress is getting induced in the model because of the temperature. So, we will understand how to perform this thermal stress analysis in Ansys Workbench. Okay. Now in Ansys Workbench, you can perform the thermal analysis and use the results of the thermal analysis as an input to the static structural analysis. The stress that is induced in the system can only be analyzed or can only be found using a static structural analysis. Because in thermal analysis, results, you will only get the thermal results, you will not get the structural results. And stress is a structural quantity. So we will have to add another static structural analysis system, and the results from the thermal analysis will be used as an input in the static structural analysis. Now we can perform these analyses separately by using the separate analysis system, and then you can use the links to connect them. The same way we saw how to connect the static structural analysis and linear buckling analysis. The same thing you can do, or else we can use the custom systems to perform the thermal stress analysis. So when you talk about custom systems, we have one custom systems option in the toolbox. There you have one option which is called as the thermal stress. So you can use this option also, which is available over here. In custom systems, you have thermal stress option. So when I double click on this and if I add this to the project window, you will see that two systems get added, thermal system plus the static structural system. Either you can use this or you can first perform the steady state thermal analysis and then link it with the static structural analysis. Okay, so we will see both the methods to understand what and how to perform the thermal stress analysis. Okay, so now we have understood what is the thermal stress and why it is induced and how it is induced in the system. Now let us see how to perform the analysis using the thermal stress analysis system. To understand thermal stresses, we will take an example of two blocks over here. If you see in the figure, we have two blocks made up of structural steel and copper alloy. The copper alloy is generating heat whose capacity is 0.05 watt per millimeter cube. Because the heat is always generated inside a volume, it is not on an area. Okay, so the heat generated inside the copper block is 0.05 watt per millimeter cube. Except the copper faces in the front and back, there is convection on all the steel faces. Okay, on all the steel faces there is a convection whose film coefficient is 50 watts per meter square Kelvin, and the ambient temperature outside is 20 kelvins. Okay, the dimensions of the model are given over here. So we will be able to generate the model and solve it using the thermal stresses analysis system. Okay, so let us see how to solve this. We will come to Ansys Workbench and we will add one steady state thermal analysis. Once the system is added, the first thing that I need to do over here is I need to add one copper alloy over here. So I will add that copper alloy so that we have both the materials ready. After this, we will enter into the geometry. The dimensions are given into millimeters, so we can set the unit system as millimeters. Okay, now we will start creating the geometry. So as per the diagram, you have 60 by 60 and this is 30. So we will come over here. I'll take a rectangle and now we will create the dimensions. This has to be 60 units and this has to be 30 units. I'll give the constraints and add a symmetry. Okay, after that come back to the modeling area and now use the extrude option to add material. But here I will say that it has to be in the symmetric manner and we will generate. So this is the first block that we have. Similarly, I will again click on XY plane, but this time I have to say that it has a new sketch and we will enter into the sketch tool and I need to create the copper block. We will give the dimensions. This has to be 30 units and this has to be 15 units. We will use the constraints, a symmetry constraint and one more symmetry constraint for this. Come back to modeling, extrude option. Now this time again I will say it is both symmetric, but here instead of adding material I will say slice material, so that the material is cut over here and another block is created. Okay, so we have two blocks now. I will rename them. This is the steel and this is copper. Okay, so we have the two blocks. You can switch off the frozen body so that you can see the blocks. Now if you wish, you can also create 1/4 of the section because it is a symmetric model. Okay, so we can also generate 1/4 of the design and we can calculate the results. Once the geometry is ready, we can exit from the design modeler and now we will enter into the mechanical window. After after you come to the mechanical window, the first thing that we'll have to do is we'll have to change the materials. So you can see that the geometry is ready. I will click on geometry over here. So for the steel block, I need to have structural steel, and for the copper, I need to apply copper alloy. So the geometry has been updated. Now let us mesh the model. So this is the default meshing that we've got. In connections, we will have one contact region, and I can have it as a bonded contact. Okay. Now after this, we will now apply the boundary conditions. So as per the problem description, you can see that the heat generated inside the copper block is 0.05 watt per millimeter cube. So heat generated is this option, internal heat generation. Select the volume. Please understand, internal heat generated can only be applied on volume. You can see all the other selection toolbars have become gray. That means you cannot select them. It can only be applied on the entire volume. Give the value 0.05. Then we also have to apply convection. So here they have said the convection is on all the surfaces except the copper front and back. So I will select all my faces over here. Okay. And the film coefficient over here, they have given it in meters, meter square kelvins. Okay. So I need to change the unit system to Kelvin first, and the unit system also I will change to meters. And now let us enter this 50 and 20. Can you see this? Okay. Once that is done, now you can add the temperature, whatever results you want to understand for thermal analysis. Once that is done, we will solve the analysis and we will get the output. Now you can see that the temperature has been generated. You can see the value of the temperature generated in kelvins. If you want, you can also check it in Celsius. Okay. So this is the temperature that is generated inside this block because of the heat generated. Okay. Now once this is done, I am interested into the calculation of the thermal stress induced. Okay. Now the thermal analysis will not give me the stress results. You can see over here. For which now we will exit from the thermal analysis mechanical window, and now we have to add the static structural analysis system to the solution of the steady state thermal analysis. So just drop it over here. You will see that all the data is getting shared, and we just have to enter into the setup now. Once you come to the static structural analysis system, now the data you can see in static structural node, you can see there is one imported load from the above analysis. So it is an imported body temperature which has been imported from here. And now in solutions over here, we can add the total deformation and the stresses that we are interested into, and we will solve the analysis. So now you can see over here, this is the stress value that we have generated. So the stress value is 3.0388 e raised to 9 Pascal. If I want it into megapascal, this is the answer. You can see the animation. Similarly, I can also check the deformation value. So the total deformation that we are getting is 1.0073 millimeters. Okay. If you want, you can use the section tool and see the results internally also. Okay. This is again a post-processing tool which we can use if you are interested into the internal results also. Okay. So this is how you will see your answers. You can see the vector plot for the total deformation also. Okay. So this is how the thermal stresses can be calculated in Ansys Workbench. In this case, we have used two different systems. We have added the static structural analysis system and dropped it on the solution of the steady state thermal system. Okay. So So this is how we will perform thermal stress analysis. The next example in thermal stress analysis that we will take is, it is an example of a simple plate. First, let us go through the problem description. A plate of length L, width W and thickness T is fixed along the width on one edge and heat flow Q is applied on the same edge. So you can see over here, one edge is fixed and on the same edge there is a heat flow of 5 watts. The opposite edge is subjected to a temperature of 20 degrees Celsius. The ambient temperature is also 20 degrees Celsius. Ambient temperature in this case is nothing but the initial temperature. Find the maximum temperature, maximum heat flux, maximum deformation and the heat reaction at the given temperature. Okay. So now let us perform this analysis. Now in this case again I will do the same thing. We will add one steady state thermal analysis. Okay. The material that we are going to use is structural steel. So now let us directly go into the geometry option. Now if you look at the dimensions of the model, L is 0.2 meters. L is 0.2 meters, W is 0.05 meters and T is 0.005. So thickness as compared to the length is very small. So I can consider this problem to be a 2D problem. Okay. So let us come into the design modeler. I will come into the sketching area and I will draw one line. We will give the dimension. This is 0.2 meters. And we will give a constraint, a symmetry constraint between this point and this point. So now this is the line that we have. Now once the line is created, we will come back to modeling and we will extrude this sketch. And the extrusion is up to 0.05 meters. That is the width. So I will say this is 0.05 meters and we will generate the surface. So the surface has been generated. The thickness of this surface can be mentioned in the mechanical window. Okay. So I will directly exit from here. Next we will enter into the mechanical window. Now we need to mention the thickness. Can you see a question mark? That means some data is missing. So I click on surface body and we have to give the thickness. So I will change the unit system to meters and now I will say units 0.005. 0.005 is the thickness. Okay. So now the thickness is also specified. Now let us mesh the model. We will use the default mesh settings. So the model has been meshed. Okay. Now let us start giving the boundary condition. So boundary conditions, they have mentioned that there is a heat flow of 5 watt and there is a temperature of 20 degrees Celsius. Now there is one more boundary condition, that is of a fixed support. Now fixed support cannot be applied in the steady state thermal analysis. Okay. So we need to apply a temperature on one edge which is 20 degrees Celsius and on the other edge there is a heat flow of 5 watts. Okay, so these are the thermal loads that can be applied in thermal analysis. After that you can analyze the temperature and heat flux. So we are interested into the maximum temperature and maximum heat flux. Also the heat reactions at the given temperature. So I can add a reaction probe at the temperature. And now we will solve the analysis. So the maximum temperature induced is 86.116 degrees Celsius. Total heat flux is 20,000, and the reaction is negative 5 volts. Okay, fine. So now we have understood the thermal results. Now close this and add a static structural analysis system to the solution. Enter into the setup. Okay. Now, according to the problem description, the edge where you are applying a heat flow, on the same edge we have to apply a fixed support. So, this is the edge where we have applied the heat flow. So, on the same edge I have to apply a fixed support. So, click on the static structural node over here and then add the fixed support to this edge. And now we have to calculate the maximum deformation. So I will add maximum deformation, total deformation over here. If you are interested, you can also add the stresses. And now we will solve the analysis. Now you can see that the total deformation is 7.7147 e raised to minus 5 meters. So if you check this into millimeters, the answer is 0.077147 millimeters. And the stress value is 173.78 megapascal. So because of the fixed support, maximum stresses are generated over here. Okay. So here we have understood that there are some boundary conditions which can only be applied in thermal analysis, and there are some boundary conditions that can only be applied in structural analysis. So it is a combination of both the analysis systems, right? So another example that we've seen for thermal stresses is a 2D problem, and we saw how to add boundary conditions from different analysis systems. Okay. Now let us look at the next example for thermal stresses. We have a cylindrical rod assembly of 4 cylinders connected end to end, has frictionless support applied on all the cylindrical surfaces, and both the flat end faces are fixed, as you can see over here in the image. Thermal and structural loads are shown below. So you can see all the loads that are acting on the body, thermal plus the structural loads. We can also see the dimension properties of the rods, and the material information is also given over here. Okay. Apart from the other loading conditions, we also have a remote force location over here. Okay, now the remote force acting on the body, the location has been given as 7, 0, 0. That means in x it is at a distance of 7. Now if you also create the model in the same orientation, you can use this coordinate system, but if you have changed the orientation of the model, you will have to change this location also. So please understand the orientation. You can see how the beam has been oriented, the assembly has been oriented, and you can perform it. Okay. Now if you feel that you can perform this in 1D, please don't use the 1D method, because there are some supports like the frictionless support that has to be applied. It can only be applied on surfaces. Please understand, frictionless support can only be applied on surfaces. So if you take this problem to be a 1D problem, you will not be able to give this support. Okay. So let us perform this analysis. We will come to Ansys Workbench, and in this case, what we are going to do is we will add one thermal stress system from the custom systems. When you do this, you will get both the systems simultaneously over here. The material that has to be used is structural steel, so I don't need to enter over here. I will directly come into the geometry. Okay. Set your unit system. It is into meters. And now start sketching. So I'll take the XY plane and I will start creating my sketches. Now please remember, it is an assembly that we need to create. So this first one is of 2 meters. You can see the dimensions over here, 2, 5, 10 and 3. from this end. Okay, so I will say this is 2 meters. We will keep it at a distance of total is 2 plus 5 is 7, 17 and 3 20. So this should be 18. This is 2 and this is 18. Okay. We will come to the modeling part. Now we will add extrude material to this. And what we can do is we can create, instead of extrude, we will use the sweep option. For that, I'm going to create a plane. Shift the YZ plane. And the offset direction is -18. Okay, generate. I'll take this plane 4. Sketching. We will make one circle whose diameter is 2 meters. Always show, and this also has to be always show. Okay. Now I will use sweep. The profile is this, and the path is this. Now from here I can directly select the faces. So select this face and enter into sketching. Again I'll make a circle over here whose dimension is 2 meters. And this has to be extruded up to a depth of 5 meters. But it has to be add frozen so that it is an assembly. Next, I am going to select this face over here and we will enter into sketching. I will say again, this is a circle. Depth is 10 meters. Add frozen. And finally, space sketching. The last depth is 3 meters. And again, this has to be add frozen, generate. So with this, we have the 4 bodies that are ready. Okay. Now let us take this into the mechanical window. Okay, so the bodies are created. All the 4 bodies have the same material, so I don't need to change the material. We have contacts. By default, all the contacts will be bonded. Let us mesh the model. We will get the default mesh settings, and the default mesh will be generated. You can see them. Now let us apply the first thermal loads. So according to the thermal loads, we have only temperatures applied on this end and this end, that is of 1000 degrees Celsius. So I can directly select temperature, select this face and select the opposite face, and on both the faces I have the same temperature getting applied. Okay, apart from this, there is no thermal load, so we can directly solve this. In this case, we will not get any temperature. You can see this. You will not see any temperature distribution because it is only one temperature acting from this end to this end. Okay, so there is no temperature distribution. Now let us select the static structural node and we will start giving the structural loads. So the first structural load that we have to give is fixed support at both these ends. Okay. Then after this they have mentioned that there is a frictionless support at all the surfaces in between. Okay. We have to give a frictionless support on all the cylindrical faces, right? So I need to select this, all the cylindrical faces. So frictionless support has been applied over there. Then there is a remote force acting at a location of 700. So let us come to that. We will add one remote force. Once the remote force is added, select the geometry where it has to get applied. Then give the coordinates. So it has to act on this, and the location is there. Value is 1 e raised to 10 Newton, and the direction should be in the opposite direction, right? So now we have the location. Next, we have to add the total deformation and the stresses induced in the model. Now let us solve this. So we can see the equivalent stress that is generated. You can see it in megapascals. It is 2260.2 megapascals. The deformation is 43.18. So the deformations and the stresses are quite high in this model because of the thermal plus the structural boundary conditions. So here we have seen how to perform a thermal stress analysis where both the loads are acting. We have thermal loads plus the structural loads that are acting. Okay. So with that last example of thermal stress analysis, we have completed the entire syllabus in Ansys Workbench. We have completed all the chapters, all the 15 chapters have been completed. Throughout the 15 chapters that we've seen, we have completed the basic fundamentals of CAE. We saw the introduction of Ansys Workbench where we understood the graphical user interface and some basic things about Ansys Workbench analysis systems, the different types of cells, how to use the cells, how to enter into the cells, all those things we've understood. After that, we understood how to create a design in Ansys Workbench using the design modeler. So we understood the sketching and modeling concepts. We also understood one important thing in design modeler, that is the use of parameters. Next, we understood about the geometry optimization, where before performing any analysis, how to change the design, how to edit the design so that it becomes simple for us or it becomes easier for us to perform the analysis and to perform the meshing. Next, we understood about the meshing concepts, how to perform meshing, how to generate the meshing. We also saw how to find the mesh quality. There are different parameters in mesh metrics like the element quality, aspect ratio, Jacobian, skewness, warpage. So all those parameters we understood, we spoke about them, we discussed about them. Then we understood about the advanced mesh settings where we discussed about proximity, curvature. Then we also discussed about the local mesh settings which can be used to control the meshing in a particular model or in a particular surface or on a particular edge or on a vertex. Then after that, we also discussed about the different types of analysis like static structural analysis, modal analysis, buckling analysis, and thermal analysis. And while we were discussing about all these types of analysis, we have solved a lot of problems, and in every problem we have learned something new, and we have seen how to use the different tools in analysis that are available. Okay. If you have any doubts related to whatever we've learned up till now, you can request for a doubt clarification on the ORG site and put all your doubts over there. Thank you.